People might benefit from looking at it one extra time in there. Comes a group of us. Right. So, old joke, but where does an 800-pound gorilla sleep? Anywhere it wants. So if you notice today, I'm taking up 3 screens. One of those screens is that 800-pound gorilla who is actually sleeping right behind me. So that's totally a thing. She has slept through about 2 hours of me listening to Iron Maiden at reasonable levels. That last song was actually Allman Brothers, but if we wake her, we wake her. No big deal. Okay, if you're here, let's get your cameras on and let's get through this. It is rather a lot of material today. So let's take a look. We're talking about polynomial functions today. A polynomial, of course, is something which has multiple terms. Every term kind of looks like this, ax to the nth, where I think n is a member of the natural numbers. So I think they made a little mistake here on this thing. So you could have x to the third, x to the fifth, but right now we can't have x to the negative second or x to the 1/2 power or anything like that. We have a whole bunch of them. Polynomial function with the form blah. There are 2 basic features of this graph that mathematicians talk about. That's me. I'm a mathematician. I'm going to talk about them. One of these is the turning point. So I don't know why we didn't start with a first degree, but as we know, a second degree polynomial can look something like that. A third degree polynomial can potentially look something like that. A fourth degree could look kind of like a W. A seventh degree, oh man, they're making note for it. So it has turns, 2, 3, 2 turns, sorry. 3, 4, 5, 6. Could look like that at least. Let's see, 1, 2, 3, 4, 5, 6. Yes, it is good. And a first degree doesn't have any turning points. Another feature is end behavior in a polynomial. The ends either approach negative infinity or positive infinity, and more on that as we go. No matter how many terms the polynomial has, the end behavior is always determined by the term with the highest power. So if I'm looking at something like this to determine the end behavior, all I need to do is look at that leading term. And especially if it's written in standard descending form, where the first term has the highest degree, then it's going to look like that. Has the same end behavior as f of x equals negative x cubed. And really, if you were to zoom out far enough, which might be pretty far, if you were to zoom out far enough, you would find that it looks an awful lot like negative 5x cubed. And the reason is that if we pick a large enough number, in some cases, large enough is 10, but in this case, definitely a billion will work. That is well large enough. The number a billion cubed is so massively large that the number a billion squared pales in comparison. In fact, it is only 1/1 billionth of the size of that. So even though this has a larger coefficient, 7, than negative 5, and really I care about the magnitude, not so much the direction. So I care that it's a 5 and a 7, not a negative 5 and a 7. It makes no difference because when x is a billion, negative 5 billion cubed is so massively large, even compared to 7 billion squared, that these terms really mean nothing. I often talk in terms of money here, just because it's something that people tend to understand. If I lost 5 billion cubed dollars, which is like more than the net worth of the planet, and then I gained 7 billion squared dollars, I wouldn't be like, oh, yeah, it's kind of okay day. No, this number is so much larger that that one is insignificant. If I had 5 billion cubed dollars and I dropped 7 billion squared dollars, I would not stop to pick it up. It is not worth my time. However long it takes me, however quick I am in picking up that billion squared dollars, I couldn't possibly spend that money that fast and run out of it in my life if I have 5 billion cubed dollars. Okay? It takes you like 3 seconds. It's not like I have an extra 3 billion squared seconds or billion seconds. It's just no big deal. Okay. Y equals x squared, x cubed. I don't know what they wanted us to do here aside from talk about the end behaviors. I'm going to talk about the end behaviors in a very simplistic manner. I'm going to say for x squared, it's up, up. Okay, there's a lot of different ways we express this, but that is the easiest one, just drawing a quick picture. And that makes sense to me. If I look like y equals x squared, it kind of looks like that. This is easier to do if I'm standing up in front of the class and can kind of do my whole arms instead of there you go. Looks kind of like that. X cubed, on the other hand, just to remind ourselves, kind of looks like this. And so it is a down, up situation. X to the fourth is up, up again. Negative x to the fourth is going to be a down, down situation. And negative x to the seventh will be an up, down situation. Sometimes we refer to this pattern just as the polynomial dance. And I don't care how many terms this thing has. I'm really, I heard the baby stir. We're all good. Scary, 800-pound gorilla there. I don't care how many terms it has. If this is the biggest term, then eventually the polynomial will graph to go up, up. Okay. So just real quick, y equals x cubed goes through 0, 0. It goes through 1, 1, and negative 1, negative 1. It goes through 2, 8, and negative 2, negative 8. It looks something like this. I tend to say it looks like a skinny parabola with one broken shoulder. This right here, oh, we've dealt with this before. That is a translation of 4 to the, I haven't heard too much from you guys. Yeah, Maddie.
Right?
Yep, and 5.
Down.
Down. Okay, so every point goes 4 to the right and 5 down, 3, 4, 5. And so we just kind of follow suit from there. Okay.
Wait, Mr. Reeves, what is the pattern for the y equals x cubed, like the coordinate?
Well, I don't spend too much time thinking about what the actual pattern is. Like I go over 1, up 1, and then over 1, up 7. And then the next one, I suppose, would be over 1 and up, because we're going to have to go to 27. It's going to be up 19. I don't know. Just get a basic idea of what it feels like. These things, especially if it's cubic or above, get off the graph so quick that I just want you to realize kind of looks like a parabola on this side, kind of looks like a parabola going the other direction on that side. X to the fifth doesn't look distinctly different. Okay. If I were to graph this one, eventually it's going to look like x cubed. So let me switch gears and let me do one of these at least on Desmos. Do I have that all set up? Nope. Nope. Yeah, Desmos. Share screen. Desmos. All right. So they wanted x cubed minus x squared minus 9x and plus 9. And like a pro, I don't actually type in x cubed. It's just so much faster to write this. So notice, and you can squish it in a little bit, if I zoom out far enough, it's beginning to look a fair amount like just x cubed. In fact, let me compare this to x cubed. Okay, at low values, not so much, but allow me to set my own x values. Let's go from negative 100 to 100. And therefore my y values, well, I'm going to get 100 cubed in here, which should be a 1 with 6 zeros after it. Negative 1, 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Notice at this window, can you really even tell the difference between the red one and the blue one? Barely. Is that fair enough? Okay. Do we agree with my analysis that if I zoom out far enough, those little humps towards the beginning are kind of insignificant when we're looking on a scale of, you know, a 1 with 6 zeros, a million. Back in. Okay, yeah, we were off here by what, about 10? What is 10 compared to a million? It's 1/100,000th, really small. Okay, so my quartic function, negative x to the fourth goes through 0, 0, goes through -1, -1, +1, -1, and 2, 16, all right, just off the graph. So even that is probably not skinny enough for what this thing did. And here I'm moving the whole thing 2 to the left and 1 down.
Did you move your paper a bit?
You bet. Kind of similar. Let's see, where's my paper? There it is. And I'm right here. Let's see what we can do with that last one. Negative x to the fourth plus 5x squared minus 4, something like that. Okay. Obviously at 0, it's distinctly different than negative x to the fourth. Negative x to the fourth. But if I were to zoom way the heck out again, and maybe we'll do same thing, 100 and 100, and give this a negative 1, 1, 2, 3, 4, 5, 6, 7. And that seems pretty good. That those two graphs are indistinguishable at this point. Okay, I think I have a hand up. I'm going to stop the share and answer. Looks like Maddie. Yes.
So when we graph these quartic functions, like, do we not have to do the weird like W thing?
It all depends. It's a great question. Right now, I'm kind of only talking about end behavior, so I'm not really talking about graphing the whole thing. Just if you zoom out far enough, negative x to the fourth with any number of weird other terms is still going to look like negative x to the fourth. Okay. Of degree 5, this one looks like degree 3. It's just even steeper. I'm sure that this is not a great drawing of it, but it's all that I'm going to do. They put in a drawing of this one, and notice its end behavior. At the end on the right, it's pointing up. At the end on the left, it is pointing down. Okay, on to the main event. And really, when I say the main event, you're in Algebra 2. Before that, you have been in Algebra 1. Here comes the fundamental theorem of algebra. So it's not just the main event for today, it's the main event for these 2 years or so of algebra. A polynomial of degree n has at most n roots. So starting with the linear functions, which are degree 1, it's a line. All it can do is hit the x-axis once. I guess unless your line were y equals 0, but that's kind of cheating. A degree 2 one goes down and then up. So I could hit it once on the way down and once on the way back up. So that right there is going to be a major thing for the rest of the year. I'm just going to put a big circle around that. If the degree of a polynomial function is even, I'm going to say the ends point the same direction. And it doesn't have to have any roots. We've seen parabolas which don't have roots. Their discriminant is less than 0. But sure, a quartic, which is one of those W's, doesn't have to have any roots either. It could be a W above the axis and continue pointing up, or it could be an M below the axis and kind of continue pointing down. If the degree of the polynomial is odd, when did I say endpoints? I'm just going to say the ends. The ends point in opposite directions. And it must have at least one root. Okay. So if it points in opposite directions, maybe you think of some point along this, this odd degree function as a starting point. Well, since it points in opposite directions, one points up, and if your starting point was below the axis, you're bound to hit it. Or if you start above the axis, the other one points down. And again, you're bound to hit it. Yeah.
Could you go to 3B just for a second?
Sure. I didn't really do much on 3B or anything.
Okay, sorry, I thought I missed something.
Nope, not at all. Not at all. I'm just kind of showing what these things could potentially look like. Okay. I want to come back to this at some point, but we have a lot to cover today. So instead, I'm going to move on. The reciprocal function. I'm going to say function and really its transformation. 1 over x. I'm not allowed to plug in 0. And I also can't get out 0. This is the exact same function, seen as it really says y equals 1 over x. I can multiply both sides by x and get xy equals 1, or I could divide by y and get that x equals 1 over y. It's kind of funky. It is the same. Oh, sorry. That's what I was doing. It is the same whether I put the x there and the y there, or the y there and the x there. Goes through the point 1, 1, and kind of does this thing where please notice that I am using one-sided arrowheads. I'm going to talk more about that in a little bit. Maybe not today, but looks something like that. It has a lot of different symmetries, I could say here. It is a reflection of itself over the line y equals x. Reflect over y equals x. It is a reflection over y equals negative x. Y equals negative x.
Can you move your paper so that we can?
Yep, there you go. It is a reflection over the origin. All of those things are true. The fact that it's a reflection over y equals x implies that it is its own inverse. If you pick your favorite number and stuff it in here, and then take that number and stuff it back in here, you'll end up back with your favorite number. The domain, I'm going to write it in the simplest form, x may not equal
0.
Yep. 0, saw some signs, heard some voices, and for that matter, y may not equal 0. All this is, in part B, is a translation 3 to the right. So actually, since they moved the graph 3 to the left, it's pretty much the exact same for drawing this thing. I'm going to draw the symmetries instead of listing them. This line, this line, and this point. The domain x this time may not equal it's the wrong number of fingers. 3. All right. I was joking. Now you have a question. Yes.
So I'm like all of a sudden I'm a little confused about what it means to reflect over the origin.
To reflect over the origin means that if I were to take a random point, let's say this one, which I will highlight like that, which seems to be the point 1/3, comma 3, and draw a line from there directly to the origin, and then draw a line continuing this line the exact same length. I didn't do such a great job, but I would end up at this point. So if the point 1/3, comma 3 is on this thing, then the point -1/3, comma -3 is on this point. Graph. I don't know why I'm saying point. Except for perhaps because that 800-pound gorilla you see sleeping in one of the squares kept me up super late. Because it's funny to go play Hop on Pop. Is that a book you guys read? Hop on Pop? No. I think it's a Dr. Seuss book. The joys of jumping on one's father, which is me. Okay, this is a standard problem that we see in different levels of math. I was working with a friend of mine, was last night? Maybe it was last night in calculus, and we actually did one of these. A piece of cardboard 10 centimeters square can be made into an open box by cutting small square from each of the corner and folding the sides up. So here is what happens. You get something which looks like this really fat plus sign. Okay, so that is after you have cut out these squares. And you fold along this dashed line and that dashed line and this dashed line and that dashed line, and you turn it into a little box with no top. I don't know how big those squares are that I cut out, so I'm just going to call them X. the whole thing was 10 centimeters to begin with, but I cut out X on this side and X on this side. So really my resulting box has a volume as a function of X, has 10 minus 2X, that's length. Oh, it's also the width squared times its height, and the height
Can
when
you
I
move
fold it
your
up
paper?
is just going to be X. Absolutely. Sorry about that.
Wait, what is X?
X is the width of the square that we cut out of the 10 by 10 square.
So wait, why are you multiplying by X?
Because once I fold this up, what is the height of this thing?
Oh.
Yeah, that little bit is X, and when I fold it up, it will have a height of X. So sometimes I start by saying volume not as a function of X is length times width times height. Well, 10 minus 2X times 10 minus 2X times X. What are the possible dimensions of the resulting box? Well, that's an interesting question because there's a whole lot of things. If X were 1, then this could be like an 8 by 8 by 1, but X could be like 0.9. And then it would be a mess. All right. So what are the dimensions of the box with a volume of 48 cubic centimeters? And we'll answer this after we complete the sketches below. All right. Quickly.
Wait,
oh,
Mr. Reeves,
Waiting. Yes.
what was the example you gave for? I don't really get the dimensions. So how do you get the dimensions for?
We can't. That's the problem. They say, what are the possible dimensions? And there's really an infinite number of them. However, it is fair to say that X has to be less than a specific number.
5?
It must be less than 5. And I think that that is really the only thing that I'm going to leave there. Because if X were greater than 5, well, then I'd be cutting away more of this box than there actually is. And that's just silly. Okay.
What about x is greater than 0?
Okay, sure. Let's do that. Has to be greater than 0. Now I can graph 0, 0 anyway, even though you would tell me to make it an open circle. I'm going to make it a closed circle anyway and say, I could make it just this. And if x equals 5, 1, 2, 3, 4, 5, we are back at 0. And not that you would allow me to put in negative values, but I think this thing is going to kind of look like, oddly enough, this. And again, I won't allow you to put in numbers which are bigger than 5, but mathematically, this equation still comes up with this graph. Okay, so I'm going to cheat a little bit. I'm going to use the old graphing calculator here. Y equals, I'll let you see what I'm doing. If I go like this, I think it looks pretty nice. Focus and clear. That's good. Y equals, what did we say? In parentheses, 10 minus 2x quantity squared times x. And I have the Italian version of the calculator. So instead of saying graph, you have to say grafissimo. Grafissimo. So it's with an Italiano accent. I actually went to Italy and they told me that that is how I should speak. It wasn't me like trying to make fun of them or anything like that. They're like, Now, if you want us to understand, you talk with your hands, go like this, and say grafissimo. The only word I learned, I took one day of Latin classes, was to say tandem bicycle, il tandem. Very nice. Yeah, Ethan.
So I know it doesn't seem like it's the case, but just to confirm, if on the graph that we made on or drew, x equals 3 is not the pinnacle of the hump, right?
I don't think it would be necessarily. I don't know. My calculator can tell me though. So I'm going to do only x's from 0 to 5. I think that's the only place that I care about. I'm making my scale 1, which just tells me to put like a little dash every one. My y minimum, -5, seems fine. We'll make this go up to about 60 or so, which will cover that 48. Now, if I go from -5 to 60 and I have a dash every one, I'm going to end up with 65 little dashes, and I won't even be able to tell, where they are. So maybe I'm just going to do a dash every 5 or so, and see if that looks about right. Okay, so I'm not seeing the top of the hump, which is okay. What I'm also going to do is I'm going to say y equals, as a different function, 48. Grafissimo. And there we go. It's going to be 48 twice, which seems perfectly reasonable to me. So I can have 2 different dimensions. I can get a taller box, which is skinnier, or I could get a shorter box, which is fatter. Either one. I can find this out in any number of different ways. These calculators are pretty amazing. I'm going to do it in a very unsophisticated manner by hitting this button right here, marked trace. When I hit trace, it puts a little cursor somewhere on here. There it is. And I'm just going to kind of get on top of it. And it says 2.99 and 48.24. Or 3 and 47. So it looks to me like the answer is just 3-ish. So again, I don't know if you can see that at the bottom where it's saying this information. At 2.99, it's like 48.2. At 2.95, it's a little bit less. There we go. So right in there. And again, that is one of the least sophisticated methods that the calculator does. So I'm just going to say that x equals 3. To find that other answer, I'm just going to hit my cursor, move that little guy until he's about there again. And this seems to be this time right around 0.64-ish, maybe 0.63-ish. Again, there are more sophisticated methods. And I didn't really answer the question. They want the dimensions. Technically, I'd have to plug it back in and figure out, oh, it's a 3 by 4 by 4. But I'm not going to do that because, as I mentioned, we've got a lot of stuff to cover today. Okay. So pushing forward, sorry about all the rush. See if I can get in a little bit of this. We are okay. Exponential growth is a function which looks like this, where x finds itself in the exponent. So if I didn't know what to do here, I could say, make myself an XY chart and say, what would happen if x equals 0? What is 2 to the 0th?
1.
No, anything to the 0th is 1. So it goes through the point 0, 1. What if x were 1? 2 to the first is 2. All right. What if x were 2? 2 to the second is 4. And I'd end up with a 3, 8. What if I went the other way? What if x were -1? What is 2 to the -1? 1/2. And over here, I get 1/4. 1/2, -2, 1/4. And this thing just starts to grow incredibly fast. Two-sided arrow on that side, one-sided on this side. And again, I'm not really going to get a chance to talk about why that is, but that's okay. Let's do the same thing without the XY chart over here. 1/2 to the 0th power, well, anything to the 0th power is 1. 1/2 to the first is 1/2. 1/4, 1/8, 16, 32nd, 64th, 128, 256, 512, and 1/1024, which is basically indistinguishable from 0 on this graph. 1/2 to the -1 would be 2, and to the -2 would be 4. This is getting super close to 0. Is it ever getting there? No, I'm getting a shaking of the head. That is where I put on that one-sided arrow to show that I'm getting super close to something. I'm not getting close to anything in particular over on the left-hand side of this graph. I'm going to go with that arrow. Okay, I think we can do this. Checking. My baby's still asleep. Awesome. Why are we not using a equals 1? The a value is 2 in this case. Well, if I used 1, what's 1 to the first? What's 1 to the second? Third, fourth, 92nd, 512. 1 to pretty much anything is 1. So it really wouldn't be exponential growth nor decay. Uh-oh. Baby stirring, baby stirring. We're okay, we're okay. Scary, scary stuff. The domain, all real numbers. We didn't plug in anything. We plugged in some negative numbers. We plugged in some positive numbers. We plugged in 0. The range, on the other hand, y in both cases was always Maddie, go ahead.
Greater than 0.
Greater than 0, not greater than or equal to. As we said, we got really close here, but we didn't get there. It was always greater than 0. What point did these two graphs have in common? Oh, yeah, Maddie again, finishes off.
0, 1.
0, 1. All standard exponential functions will pass through the point 0, 1. Even if I had 1 as my base. I have 3 as my base. 3 to the 0th is 1. 7 to the 0th is 1. Anything to the 0th is 1. Oh my goodness. Did we get there? We did. Okay. It was a whirlwind kind of day. That's why I recorded this. So if there's parts which we went over super quickly, of course we can repeat them in class the other day. Oh, I guess my phone just ran out of batteries or something. It's interesting. We can, of course, repeat it another day in class or anything that you guys need. But for the time being, we did it. Okay, guys, have a great afternoon. I will check in on you. My schedule says we don't meet tomorrow. Is that the thing?
Yeah, we don't.
We don't. Okay, so I'll see you guys again on Friday.
Thank you.
Thank you.
Bye-bye. Bye-bye.
Thank you. Wait, will you send us the video, Mr. Reeves?
Of course, yes.
Thanks.
Or a link to it.
Sorry I was late.
No worries. No worries. You're one of the reasons I recorded it.